do this one, and we'll talk about the other one tomorrow. This one's easy. I want you to compute the impulse by finding the change in momentum. You can't do this side because you don't know how long the ball is in contact with the ground, nor do you know the force from the ground. But you can do this one. But to do that one, you actually need mv final minus mv initial. I'll give you the mass of the tennis ball tomorrow if you didn't already take it. But you should be able to calculate v final and v initial from the heights. I'll give you a hint. mgh equals 1/2 mv squared. So you can use the drop height to figure out the initial velocity. This is how fast it's going when it reaches the ground. And you can use mgh equals 1/2 mv squared for when it recoils to find the final velocity. You did it from two different heights, so I'd like you to calculate two different impulses. Okay? This one's pretty straightforward. Any questions about what you're supposed to do on these three evaluations? Now there's quite a bit to do here, and it's varied. So I've taken a video of what we've just talked about. And this one's going to take me too long to explain, I believe. So first, in order to evaluate your data, I want to talk a little bit about what this was. This is a two-dimensional collision. And we used a projectile launcher as a means of giving us a consistent, even velocity every single time. So you started the ball probably against the pin every time right here, and hopefully released it the same way every time. Based on conservation of energy, the ball should have acquired a velocity that was the same for every single throw. Now, when there was no collision, you could use projectile motion to figure out how fast the ball was going. We're just using the simple tenets that if the ball were to fall from this height, you can figure out how long it takes to reach the ground by just executing the square root of 2h over g. And using the rules of projectile motion, something like range equals t, you could figure out how fast it was launched. Now, you have access to figure out what the range was. And with the height, you could figure out the time and calculate the velocity of the ball just before the collision. Now, the truth is, you don't have to calculate the time. Because the time is the same whether there was a collision or wasn't a collision, you're going to be dividing all of these numbers by the same number. So we can just compare the ranges and make the comparison that whatever comparison we get from the ranges is applicable to the velocities, because they all would have taken the same amount of time to drop, because even if there was a collision, they all were falling from the same height. Everybody follow that argument? So instead of finding the velocity, all you need to do is find the ranges. Now there's going to be a range in this direction and a range in this direction. This one I'm going to call the velocity on the left, and this one the velocity on the right. So when you put the ball in play and had a collision, the ball should have gone and made some kind of pattern that looks like this. Now, you're measuring to the center of the patterns here. Just draw a circle around all the dots and mark the center and draw a line into the center. What you need to show is that the momentum in the y direction didn't change and the momentum in the x direction didn't change. Now, the ball had no momentum in the x direction because it was traveling in a straight line before the collision. But it does have momentum in the y direction. So, take and figure out how much of the velocity is in the y direction for the right ball, and how much of the velocity was in the y direction for the left ball. You're just going to be drawing a triangle here, because you're also going to need to find how much of the velocity was in the x direction for the left ball, and how much of the velocity was in the x direction for the y ball. So all you need to do is draw in a right triangle on both sides. Measure this length and compare it to this length. They should be equal. Then you want to compare this length and this length. Not compare, you want to add those together and compare it to the length with no collision. The velocity in the y direction should add up to the initial velocity, and the velocities in the x direction should be equal and opposite. In doing that portion, you should probably calculate a percent difference to see how close your data actually is. So to make it look mathy, I would say velocity to the right in the y direction plus velocity to the left in the y direction should equal v naught. Should. You're trying to see if they are. And the velocity on the left in the x direction plus the velocity on the right in the x direction should sum to be 0. Should. They should be equal and opposite. Now, I would just do a percent difference calculation to see how close they are. Raise your hands if you need me to tell you how to do a percent difference calculation. So all of you know? Good. So you should be fine. I would expect it to be within about 5%. If you took your data correctly. I think that if it's within 5%, you could probably successfully say that you demonstrated conservation of momentum. So for each one of these discussions, you're going to be trying to demonstrate something. So for this one, you should state whether you demonstrated or didn't demonstrate conservation of momentum by calculating a percent difference and seeing if your percent difference was less than 5%. If it was, I think you successfully showed it. Now, I'm assuming you can calculate percent difference. All of you said you're good, but just in case, if I was to use this one as my example, VLX minus VRX, take the absolute value and divide by the average and convert that to a percentage. That's how you calculate percent difference. Just making sure. I did it for that one, and be similar to this, you would compare this number with this number. That's what you'd be comparing, which means subtract them and take the average. All right, I'm gonna move on to one of the other ones, okay? This is one though where that piece of paper is big. Once you get all of this drawn on it, you're not turning that in. Get all of this drawn, show your measurements, and then take a picture of that and include it with your lab. And you can put this in the trash. Does that make sense? So I want the picture of this that you take from your big piece of paper. All right. Let's do this one since so many people had so much trouble with it. Not calling anybody out. So let's say that you're doing the one where the green car is at rest and you push the yellow car. So the yellow car has some velocity, there's a collision, and then has some velocity afterwards. The green car would have no velocity and then would have some velocity afterwards. What these velocities are will depend, of course, on how much mass the cars have. But what you really have here is the initial velocity of the yellow car and the final velocity of the yellow car, and the initial velocity of the green car and the final velocity of the green car. you should see if the momentums are equal before and after the collision. That would be momentum of the green car before the collision plus momentum of the yellow car before the collision. Is it equal to the momentum of the green car after the collision plus the momentum of the yellow car after the collision? Just a reminder that momentum equals v. So read the velocities off the graph. You know what the masses were. And again, calculate percent difference between the left side and the right side. This one should be really close. You should get well under 5%. But there's something else I want you to do. The acceleration graph should have something like this. Right? I want you to calculate the impulse for each. Find the area here, and then multiply by the mass of the car. If you do that, what you're finding is net force times time. You're finding the impulse. And do that on both. These should be equal and opposite. So, again, use percent difference to see how close they are. Again, these should be very close. I'd like you to do that for all three graphs. The explosion one will look not like this. It's going to look a little different, but not much different. The only difference is that it's going to show both cars having zero velocity before, and then one having a positive velocity and one having a negative velocity after. But you should still get something that looks like this. All right? Any questions about what I want there?